other synonyms that we had for solutions. We had lots of words we could use. Sorry, it's going to blink. There we go. We had several options that meant the same exact thing as solutions. What were some of those? Roots. Our x-intercepts. There we go. There we go. That's an N. Spelling is a suggestion. There we go. Now it's an N. Roots, solutions, x-intercepts. One more. One more. What was? Zeros. Good. I was rolling my eyes at the 8th graders thumping into the wall over there, not any of y'all. Once they get bused up here to take geometry because the middle school doesn't have it. Only one of the middle schools has geometry in the building. So they bust up over here. All right, so these are synonyms for it. I use those words a lot of times interchangeably. You're going to hear them enough times you get real sick of them. But they all mean the same thing. There's supposed to be a grown-up over there watching them, and they don't. So much fun. So then we're going to look down here, and we're going to find our solutions, or our roots, or our zeros, or our x-intercepts, which that makes it really easy to figure out what we're looking for here on our graph. So where do we have solutions on this graph? At 2, 0. So this guy here. Where else? And negative 4, 0. So we can do them as ordered pairs like this, 100%, valid way to write them. Or you can say when x equals negative 4 and when x equals 2. You cannot just put negative 4 and 2. That's not enough information. So you got to tell me x equals negative 4 and x equals 2, or put them as ordered pairs. Either way is fine that way. So then let's think about these square roots over here. It's been a minute since we looked at square roots. What is the square root of 16? 4. How do we know that? Because 4 squared is 16, right? So the square root of 4 squared, the square root and the square cancel out, so we just get 4. 16 is the same thing as 4 squared. So you can write it like that to simplify things. If I find a perfect square inside a radical, we can simplify it. You also may have done this with the birthday cake method. Some teachers went with the birthday cake method. You do not have to, though. How about 50? What could we do with 50? There's a 25 inside 50, right? I could rewrite 50 as 2 times 25. That means the same thing. I didn't change anything except how it looks. Then what I can do is I can actually break those up into 2 little baby chunks. I can do the square root of 2 and the square root of 25. Why do we like that better? What is the square root of 25? 5. We like this better because I know that one. This thing is 5. Can we simplify the square root of 2? Is that a thing we know? It's icky and decimally. If you put it into the calculator, it'll either just spit back out square root of 2, or it'll give you a gross decimal. So we just leave that as the square root of 2. So when we put this in our answer, we're going to put our whole numbers in front, and then our radical, which is the other way around for you. Whole numbers in front, and then the radical. So it's going to be 5 square root of 2. It'll simplify. This is called our simplified radical form. It's as small as we can make these numbers. So you may have done birthday cake method back in the day, where we put our big number on the bottom and we divide out primes. Divides by 2 and we get 25. Divides by 5 and we get 5. Divides by 5 and we get 1. Happy birthday! And we find our pairs. If that is not familiar to you, ignore that. If that is familiar to you, it still works. Exactly for what we're doing today. But there's like a cluster of middle school math teachers that still teach it that way. It's not as common as it was like 5 years ago. But I was just tossing it out there because you may have seen it that way, and sometimes all we have to do is see it again and go, ah. Okay? I am, for the most part, going to do this way because it makes more sense with what we're doing in class with square roots. But if you like the birthday cake method or factorization trees or whatever other method you have, it's probably still going to work with what we're going to do today. Because what we're going to do today is a little bit weird. Because thinking through square roots and what we can do, there was one thing we really could not do in square roots, where we would get an error on our calculator and your middle school math teacher says you can't do it. Do you remember what it was? What can we not take square roots of? What if I have to do a square root of a negative number? If I have you type that in the calculator, what would it say? It gives you an error. The calculators can't do this. So this is something we have to know how to do ourselves. This is a concept that we're going to work with, and it's going to happen a lot in this chapter, and it's going to pop up in some of the others, and you're going to see these in most math courses you take from here to whenever you stop taking math. So I'm using them in my grad school class right now. My entire grad school class is about this concept, but just like in way weirder ways. But we're going to work with something called an imaginary number. Because the one thing we've never been able to do before now is to do a square root of a negative number. And so what we're going to do is we're actually going to address this the same way we did like the 50. And I'm going to pull out pieces that multiply separately. So we're going to start with this square root of negative 16. We just did positive 16 in the bell work. So I can split this up into pieces that make my life easier. So if I take the square root of 16 and I make it be negative 1 times 16 and split it into 2 different pieces, then I can split that into 2 different radicals. That's what the square root symbol guy is called. So I can make this be the square root of negative 1 and the square root of 16. We like this better because what is the square root of 16? 4. I know this guy. This thing is 4. It is what it is. It's 4. But then we're stuck with that square root of negative 1, which is super icky. Like that is a thing we can't do. And in fact, that's a thing we can't do. That doesn't exist. It's not real. It's not a real number. That is an imaginary number. In fact, it is the imaginary number. So our important piece for today, our whole focus on what we're doing, is that the square root of negative 1 is imaginary. And so since it's not a thing that exists, we gave it a name. It is the one letter we have never used as a variable in any problem ever, ever, ever. Because it makes my brain hurt if we try and use it as anything other than what it is. And that is the letter I. So the square root of negative 1 we call I. And so down here on our square root of negative 16, we're going to take this square root of negative 1 and we say, hey, this guy we called I. So this is the same thing as saying I times 4. The reason we have this is because mathematicians back in the day were trying to solve quadratics, these guys we've been working with, and trying to find our solutions. And when they had the graphs that looked like this, where we have no solution, they'd get stuck halfway third solving the problem, and it irked them. It bothered them that they could not get to the end of an x equals and get like an actual answer. They were stuck. And so they made up I. They called it the imaginary number to be able to finish those kinds of problems. Imagine being that bored. Those are the days of pre-internet. Being that bored that you make this up. Turn the music off. Thank you. So, I heard it again. You can have your answer written here as I times 4. I am 100% okay with that. I times 4. I'm going to switch it so it's the numbers in front of the letters just because it's better math grammar. But if you put it as I4 or I times 4 instead of 4I, I am 100% okay with that. I'm just going to switch them around so it's numbers, then letters. If we have them, then radicals. Just like if we said X3, it feels weird. Saying I4 feels weird unless I'm talking about a highway. So 3X, 4I, that same kind of vibe. So we're going to start by just practicing simplifying these radicals of negative numbers to put them as imaginaries. Okay? Questions on this first one? I know these are weird. Okay, let's do this same thing with our negative 75. We're going to break it up into chunks, trying to find something in there that's a perfect square, or finding a pair of numbers that we can make a perfect square. So, we're going to take our negative 75 and break it up into some chunks. I'm always going to pull out that negative 1 so I can deal with the 75 on its own. Does anyone see a perfect square inside 75, like a factor of 75? Or does anyone see something that 75 can be divided by? 5. It divides by 5. So 75 is 5 times what? 15. I heard it. 15. 15. Could we break that down further? What multiplies to make 15? 5 and 3. So 5 times 3 is the same thing as 75. You can absolutely write it like this, because where do we have two pieces that we could make a perfect square out of? The two 5s. 5 times 5 is the same thing as 5 squared. So I could also write this as my square root of negative 1, square root of 5 squared, and then my square root of 3, he's just stuck by himself. He doesn't have any friends. He doesn't get to go outside. In radical land, you can only come outside with a buddy. It's kind of a rough neighborhood. So writing it like this will sometimes help, because then I can see that my square root and my square cancel out. Those are opposites of each other. That's how we undo one. So the square root of 25, or the square root of 5 squared, is just going to be 5. Can we simplify the square root of 3? No. It's another one that's a gross decimal. If it doesn't have a perfect square in it, we've got to simplify it. We can't simplify it. And then our square root of negative 1, that's the piece we call I. And again, I am 100% okay if you put it in that order and leave it right there. I do want our radical piece to be the very last one, just so it's really clear what is inside and what is outside the radical. But if you have it as I5 instead of 5I, I'm 100% okay with that. What I don't want you to put is square root of 3, I5. Yes, dear? Because we had a squared 5. I had 5 times 5.
Okay, so it gets to come out.
So the square and the square root cancel each other out. It's like when we add and subtract to get something to be 0. The square and the square root cancel each other out. Yes, dear? Yes, I'm going to let you pass. What's up? I do have graph paper. I can use some. So I'm going to write this as my 5i square root of 3, just because it makes my brain itch if I don't. And Logan, on this bottom, this third shelf right here, I have graph paper. Okay, any questions on these before I change the page? to my page, and then I'll write. Ooh. Guesses. Okay. It's music box. All right, so we're going to do 2 more like this to practice it. So I want you to see if we can find the pieces in here that are perfect squares. Where could we find a perfect square in here? All right. So when we're looking at the square root of 294, we're going to break this up into pieces. So we're going to have our -1. And what does 294 divide by? Like, how can I break that down into pieces that are a little smaller? Well, it ends in a 4, so that means for sure it's even. So it'll divide by 2. If I divide by 2, we get left with 147. Can we divide 147 by anything? Do you guys know the trick how to tell if something divides by 3s?
How is it you can divide by 7?
You can. But if we go by 3s, it actually shows us something else. Do you guys know the trick for how to tell if something divides by 3? If you add up the digits, 1 plus 4 plus 7, we get 12. Since 12 is divisible by 3, 147 is divisible by 3. So if when you add them up, it's divisible by 3, that number will be divisible. So it saves you a little bit of step. Or you can type it in the calculator. But 147 does divide by 3. And what do we get when we divide 147 by 3? 49. What do we know about 49? It's 7 squared. It's a perfect square. We love perfect squares. Perfect squares are our favorites when we're dealing with square roots. Because I can stop right there. I don't have to go all the way down to individual factors. I can do square root of 49. We know that. So I'm going to break this up into some pieces now to have my square root of -1 over here. My 2 and my 3 don't have any friends, so they're going to go in the house together. They're going to stay inside. My 2 times 3. And then I'm going to put my square root of 49 in its own place. Because I know I can do that square root. We know that. 49 is a perfect square. So square root of -1 is what we call what? What do I call this piece? I. Can I simplify this? The square root of 2 times 3. It's just going to be square root of 6. And then what's our square root of 49? 7. So I have I times the square root of 6 times 7. We got to put that 7 out in front. Do not put numbers behind your radical because it's way too easy to forget where that radical ends. So I'm going to put this as my 7I square root of 6. If you put it as I7 square root of 6, that is also okay. I'm going to raise that curve, the line up a little bit just to stop billowing, but it's really warm today, so got the window open. It is like 9 degrees. And it's cooler out than in. All my watch will tell me is that it's windy though. At 67. So yeah, it's cooler out than in. All right. One more like this before I show you why the heck we care and where this came from. So let's do our square root of -24. Same kind of vibe. I'm going to split this up into some chunks. -1. How can I divide 24 into pieces? trying to find us a perfect square somewhere. What are some things that multiply to make negative, or that multiply to make 24? We could pull 6. 6 times what? 6 times 4. Does 6 have any perfect squares inside of it? Factors of 6, we just have 2 and 3. So I don't have any pairs in there. But 4, is that got something I can take a square root of? Yeah, 4 is a perfect square. So we can split this up into these pieces. I've got my square root of -1 and my square root of 6 and my square root of 4. You can also split that up if we need to have that be -1 times 2 times 3 times my 4. Just to find those pieces. What's up? We divided 24, trying to find a piece that had a perfect square in it. And so someone spotted that there was a 6 that would divide out and leave me with 4. But you could also do the same thing we did before, where I took a 2 and have it be 2 times 12, and then divide that by 2, and then 2 times 6. And I could see that that would be a 4. You can break it down however you want, but we're just trying to find a perfect square in there somewhere, so that we can divide that out and simplify it. Because we know the square root of 4 is what? 2. Can we simplify the square root of 6? It doesn't have any perfect squares in it. That's an icky decimal. So we're just going to leave it as square root of 6. But our square root of -1, that's the reason we're here. That's our I. So putting this in the order we need, numbers in front, that radical has to be last. It has to be last. So we can write this as 2 times I square root of 6. You can put I2 square root of 6. I don't care what order it's in, but the radical has to be last. Has to be last. Okay. Questions on this bit before we see where this came from and why the heck we care? Just doing a really quick adjustment. Okay, so I'm going to give us 3 little example problems so that we can look at this and see why we care. So we're going to start with the left one, and we're going to try and figure out what x would be. So this one is old school. If I want to know what x is here, what should we do to get x by itself? Add 81. So if I add 81 to both sides, we're going to have x squared equals 81, right? How do I figure out what x is? Square root both sides. So I can square root both sides. When I do the square root of x squared, my square and my square root cancel out. But what do we need to remember when we are solving this? What are my options for x? X could be what? What is square root of 81? 9. What else, when squared, gives me 81? -9. So when we're solving in equations, it could be that we have a positive or a negative. So we usually say plus or minus just to save ourselves some writing. So when we're in equations is when we're going to have that plus or minus. If we're working with radicals on their own, we're not going to focus on the plus or minus. We're going to deal with, it's called the principal root. It's a thing, but I'm not going to worry about it. But radicals on their own, no plus or minus. Equations, plus or minus. So then let's do this middle one. It's very similar. But this time it's x squared plus 81. So what do I need to do to get my x squared by itself? Subtract the 81. So we're going to subtract 81 from both sides. So that's going to give me that x squared equals -81. And what do I do to get my x by itself? Square root both sides. So we're going to square root this side and this side. Again, my square root and my square cancel out over here. So we're going to have our x equals, I did the square root in an equation. I took the square root of x, so that's when we include our plus and minus. What is the square root of negative 81? 9i. So this one has imaginary roots. So this has roots 9i and negative 9i. So we still have two solutions. They're just not real. They're imaginary roots. So we still include the plus or minus when we're dealing with equations, but sometimes we get imaginary roots. These kinds of problems are why the I was invented. Because if we didn't have I, we'd be stuck right here, and that bothered people. Oh, we're doing it on time. Cool. So let's do this third one up here. What's going to be our first step on this third one? Our 3x squared plus 27 equals 0. What do I need to do first? Yeah. We're going to start with getting our x squared by ourselves. It's very similar to our absolute values in that way, where I want to get that chunk isolated. I need to isolate my x squared. So we're going to subtract our 27 from both sides. And that gives me 3x squared equals negative 27. Then what can I do? Yeah. I still want to get my x squared by itself, so I don't want a square root right here because I don't want to have to deal with the square root of 3. Ew. So let's divide by the 3 to get my x squared all by itself. So we're going to divide by 3. That's going to give me that my x squared equals, what is 27 divided by 3? Or negative 27 divided by 3? Negative 9. Lots of 9s on this page, sorry. Then what do we do? Now we can square root it. I've got my x squared all by itself. So we are going to square root here and here. My square root and my square cancel out. So we're left with our x equals, we're in an equation, so we use our plus or minus. What is the square root of negative 9? 3i. Okay, and if you still want to break them apart and find our little pieces in our factors, totally fine. But we're going to wind up at the square root of 9 is 3, and the square root of negative 1 is I. Okay? Questions on this part? I have one more little bit for us. Little bit. Okay? So we're going to go out of the equations and back into our radicals, and we're going to start taking a couple of radicals and combining things together. So we have one last piece to see. So we're going to look at a couple of pieces like this. So if I give us a couple of radicals and we are asked to multiply them together, what I'm going to do is I'm going to break them into their factors and then rearrange some things to see if it makes my life easier. Because we're looking to simplify each of these. I want to simplify them down into their imaginary components and their real components so that we can simplify the whole product. So when we're looking at things like the square root of negative 10 and the square root of negative 15, what I'm going to do is I'm going to break down my square root of negative 10 to be my negative 1 times, what can I do that multiplies to be 10? 5 times 2. So 10 I can break down into the factors 5 times 2. Is there anything in here I can do to simplify as it is right now, like perfect square wise? There's nothing in there that would simplify. So let's see if doing the 15 at the same time will help. So if I do the square root of negative 15, we're going to have negative 1 times what? How can I break 15 down? 5 times 3. 5 times 3. Well, when we were looking at these individually the first time, I would take each of these factors and kind of chunk them up into their own radicals. Because then what we can do is we can actually move these around. Think of this all as one gigantor radical. What we have here, I'm going to break these into our individual pieces. I have square root of negative 1, square root of 5, square root of 2, square root of negative 1, square root of 5, lots of pieces here, square root of 3. So all these chunks. Do I have any pairs in here of numbers where we know the square root of them? I have 2 5s. I have the square root of 5, and later on I have the square root of 5. So what these two pieces are, if I was to combine them together like term style, I have the square root of 5 squared. I have 2 of them. I also know what this guy's called. That's our new piece, our square root of negative 1. That's our I. This guy too, this is another I. And then we have these 2 leftover chunks. I have my 2 and my 3. They don't have any buddies, so I'm going to put them in the same house so they're not lonely. My 2 and my 3. So the reason I like to do it like this is because then we can see that our square root and our square are going to cancel out here. Whether it's outside or inside, it does not matter. So we have 5, and I have I times I. How could I write that? I squared. And then we have the square root of 2 times 3, which is 6. I squared looks weird though. What does I mean again? What does I stand for? It's the imaginary number. So what does I equal? Not negative 1, equals the square root of negative 1. So if I look at I squared, we have the square root of negative 1 squared. If I have a square root and a square, they cancel out. So I squared is the only thing in the entire existence of the universe that when squared gives me a negative number. Because I squared equals negative 1. Because I is the square root of negative 1. So down here, I squared actually equals negative 1. So this guy is negative 1. So our whole thing down here, I've got 5 times negative 1 times the square root of 6. We've got negative 5 square root of 6. And I know they're ugly and unpleasant. But that's our answer. I is the only thing that when squared gives me a negative number. Ever, ever. Goodness, how did I miss that email? Questions on this one? We're going to do another one just to practice this one more time. That's the last one, I promise. So we're going to simplify these first. And then we'll see what's going on. And then we'll do that, I promise. So how can I simplify the square root of negative 16? What does this simplify down to be? 4i, because that negative sign makes it an I. How about our square root of negative 25? It's 5i. So we don't wind up with any radicals on this one. Those are both perfect squares. So what I have is 4i times 5i, because that's what this guy is.
should get to the lowest number that.
Yep. It's the perfect square that's inside of it. That's what we're doing. So if I multiply 4i times 5i, what are we going to have? Yeah, 4 times 5 gives me 20. Think about it if it was 4x and 5x. We would have 20. And then we'd have our I times I, which gives me I squared. Oh, but we just looked at I squared. What does I squared equal? It's the square root of -1, then squared. So I squared actually equals -1. So my square root of -16 times the square root of -25 is going to have an answer of -20. Because I squared equals -1. That means the same thing. So I's are weird. They're weird. But they're going to come up like a lot this chapter and then sporadically for the rest of the year. And they will continue in your math courses until you stop taking math courses. And if you decide to go back to grad school as a grown-up, sometimes you will take a class where you do calculus with only imaginary numbers. It's my current grad school course right now. Is I'm taking these guys and then doing calculus with them. Ew. Okay. Questions on this bit? Or on any of the things we did right now? So, I'm sorry. I have another homework for you.
Wait, pause.
Pausing. What?
So when's that one due? I'm not gonna lie, it's too much homework.
Last one of the week, I promise.
So okay, that's due Monday.
Yeah.
And then what you gave us yesterday is due tomorrow.
Due tomorrow.
Okay, so
I give you 2 days on all of them. On all of them.
okay, well,
So I gave you one of them. I mean, I always give you 2 days. That doesn't mean I don't give them to you in sequential days. To be fair,
Oh wait, I found my phone.
I didn't plan this chapter. The chapter I planned, I promise, does not overlap. But I didn't plan this chapter. But the chapter I planned, there's no overlap, I promise.
So I was gonna be privileged.
But we make ours.
I was gonna be like a mix of
So the front side is what we just say. The back side is what we're going to do tomorrow. I promise the back side looks
That should have
tomorrow.
very good experience.
That is not bad.
Yeah, the prom has to be at.
I promise, I promise.
The closet and finance stuff. Okay. Wait, I could be